for them. All right. Okay, last week we were at page 25. We actually already did part of page 25. We already did part A, part B, and then part B1 actually. So page 26 regarding the calculations is where we actually did not do. So I'm just going to go through it very quickly, plus another question before we go on to ideal guesses. So let me just open out some of the questions. So this is November 18 P42. Right, this is November 18 P42 question 3. Okay, right, before we go to the question, let's just recap a little on what the question was actually about. Here they tell you that a student is setting up an apparatus as shown in the figure below to investigate the melting of ice. They tell you that the heater is switched on, and then when the pure ice is melting at a constant rate, meaning say constant melting rate, the data in the figure below is shown. You have the voltmeter reading of 12.8, you have an ammeter reading of 4.6, you have the initial mass of the beaker plus water as 121.5, and the final mass of the beaker plus water as 185. And then after that, the time of collection was actually 5 minutes. Now, you see that this initial mass of the beaker plus water and the final mass of the beaker plus water, there's actually a difference here. So what does the difference in mass actually represent? The difference in mass here actually represents the mass of water that has actually melted, because you are measuring this mass here right now, and the mass here is actually due to whatever water that has melted from the ice and is collecting at the bottom here. So you are actually measuring the mass of the water melted, and then the difference here between the initial value and final value is actually the mass of water that has been added on due to the melting of ice. Okay, so it's correct to say that this is the mass of water that is actually melted at constant melting rate. Okay, so that time I mentioned to you, you really only start to bother about collecting the masses when you have reached constant boiling rate or constant melting rate. All right. Okay, so let's look at the second part of the question. They are asking you right now, use the data from figure 3.2 to determine the rate at which thermal energy is transferred to the melting ice. When they tell you the rate, this one already means per unit time. Okay, they want it in terms of per unit time. So when they say the rate at which thermal energy is transferred to the melting ice, they want it in joules per second. In other words, is in watts. Okay. So what is the thermal energy transferred to the melting ice? What is the amount of energy that has actually been absorbed by the ice in order to melt? Now this one you actually don't need to use your energy equations like you did last time. Last time we mentioned to you that if you're talking about the energy equation, for the case of melting ice, it was mentioned that heat supplied by heater plus heat gain from surroundings will be equal to the heat to melt the ice. Okay, now you don't really need to use this equation at this stage, not yet. All right, the question is asking you thermal energy transfer to the melting ice. They're actually asking you to find this one. Okay, while it's correct to say we can use this equation to find the heat to melt the ice, there's a problem here right now because we do not know what is the heat gain from the surroundings. Okay, this one is unknown, so we cannot use this equation as it is to find out the heat to melt the ice. The question never told us what is the amount of heat gain from the surroundings, so we cannot do this we cannot use this equation. Okay, we do know the heat supplied by the heater because we have the value of V and I, the value of the voltage and current from the previous page, and we also have the time. So this one we can actually find out. All right, but we cannot proceed right now with this current equation. So the only way we can actually proceed now is if we use a separate equation to find this one. Now this one, you can actually use Q is equals to ml. Okay, if you know the specific latent heat of ice and you know the mass of ice that is actually melted, you would be able to find out the amount of heat required. Okay, there's a separate equation that you can use directly, provided you know the specific latent heat. Okay, so if they want it in terms of per unit time, you just really divide by T so that you get Q over T equals to ml over T, which is actually what you are doing here. ml divided by T, you take the difference in the masses, which is actually the mass of water melted, sorry, mass of ice that has melted, and then multiply with your specific latent heat divided by your time taken, which is 5 minutes. Remember to change it to seconds. Okay. Your specific latent heat, I think they gave it to you somewhere. Wait, let me see where it is. Where did you give? Yeah, they already gave you the specific latent heat as 332 joules per gram. Hi, Janody. We are at page 25. We are actually doing the remainder of the question from last week. We're actually at page 26, sorry. Okay, so yeah, back to what I was talking about. We already know the specific latent heat. All right, this one was in joules per gram. So this one here, the mass, you can just leave it in terms of gram because you see the mass, the units will cancel off. There's no need for you to change from gram to kg. Just leave it as it is. All right. So eventually your final answer would be 70.3 watts. Okay. Right, so this one is okay. Then if you move on to the next part of the question, what is the thermal energy that you have actually gained from the surroundings? This one is actually talking about this one right now. Okay, they want the thermal energy or rather the heat energy gained from the surroundings in terms of per unit time again, right? So in your case here, this is where you actually would need to use this entire equation, okay? Because right now, the heat gained by the ice to melt, this one you know. The heat supplied by the heater is also something that you know. Okay, so given that you know these two, you can now work out what is the heat gain from the surroundings. So you use the equation, but in terms of per unit time, so you are going to get power equal power plus heat gain per unit time equals to ml over T. Okay, so in your case, heat gain per unit time would equal to ml over T minus power. Power in turn is VI. Okay, because they want it in per unit time now, which is joules per second. It is actually talking about power. Okay, you just take the power as the product of voltage and current. Your ml over T, this one is actually what you actually found above here. Okay, there's no need for you to go and substitute in the values again and redo this. You already know that this one is this one right over here. Okay, so H over T, heat gain per unit time, will be 70.3 minus with 12 times 4.6, giving you the answer as 11.4 watts. All right, so this is for this particular question. Done. Okay, then we do one last question before I go on to ideal gases. This one I think is something that we've done before, but I think we can go through it really quickly. Wait, 25 we've done. Okay. Oh, sorry, not really something that we've done before. Okay, can you guys just go on to page 9? We'll just go through this one and then after that we'll be done. Just have a look at page 9. This one is March 2016 P42. Okay. Now, so there are some things here that we can probably skip. If you look at your worksheet under page 9, the first part is state what is meant by internal energy. Internal energy is just basically whatever that you have in your notes last time, where we tell you it is the sum of a random distribution of kinetic and potential energies of molecules in a system. You can just make use of the definition from the notes. What I have written here is written a different way, but they mean the same thing. But I'd rather you just write the definition in the notes. Okay, you can just copy it from your notes later. You already know what internal energy is. Okay, of interest to you is actually question 3. All right, this is the bulk of the question. Now, define for us what is specific heat capacity. Okay, it is the heat energy or thermal energy per unit mass required to raise the temperature of a substance by 1 degree. Okay, you can write it as this heat because you know that Q is mc delta T, right? C is Q over m over delta T. So it will be joules per kg per Kelvin or per degree centigrade, whichever it is. Okay, so it's thermal energy per unit mass to raise the temperature of a substance by 1 degree. You can actually kind of write it in a simplified manner where you just say it's heat energy needed per unit mass per unit temperature rise. That's fine. Okay, now because this one is definition of physical quantity, you should never ever include units. Okay, do not include units when it comes to definitions of physical quantities. If they ask you to define units, then yes, you will include units inside your answer. But if it is a physical quantity definition, you do not include units inside your answer. What I mean by that is that in IGCSE or SPM, you guys might have defined specific heat capacity as this, where you say is heat energy required to raise the temperature of 1 kg of substance by say 1 Kelvin. Okay, so this one you see 1 kg is unit of mass. 1 Kelvin is unit of temperature. So if let's say your definition now includes units inside, this one will be considered as wrong. Okay, the wrong part is the part where you included units. You must write them in terms of physical quantity. Here, if you write it in terms of physical quantity, it will be heat energy required to raise the temperature per unit mass of a substance by one unit of temperature or by 1 degree of temperature. Okay, you see those do not have mention of units inside. Okay, now for part B, we tell you that a student carries out an experiment to determine the specific heat capacity of a liquid using the apparatus that is illustrated here. Liquid enters the tube at a constant temperature of 19.5 degrees and then leaves the tube at a temperature of 25.5 degrees. The mass of liquid flowing through the tube per unit time is m. Okay, just make sure you know that this m is actually in terms of per unit time. Okay, the electrical power P dissipated. The electrical power P is dissipated in the heating coil. The student changes M and then adjusts P until the final temperature of the liquid leaving the tube is 25.5 degrees. Data shown in the figure below are obtained, where they tell you if you use this power, this is the mass per unit time that actually flowed out of the tube. And then you change the power to 44.9. This is now the new mass of liquid flowing through the tube per unit time. Okay, so just bear in mind that your liquid is flowing in like this and going out like this. Okay, and is being heated by your heating coil here. So one of the things that they mention here is that, you see, for both cases, have same inlet and outlet temperature. Okay. In other words, same temperature difference. Okay. Because you see, they change the power, but then at the same time, they maintain these two temperatures here. Okay. You can just think of it as they're actually kind of maintaining the same temperature difference between the two between the inlet and outlet. So when the question asks you next, suggest why is it that why would the student actually obtain two values for M rather than just one value? What's the reason the student would actually try to obtain two different value of the masses? Now, since you've actually done the part where we tell you how to determine the specific latent heat or vaporization from the nodes, you would already have an idea that one of the reasons why you go and change the power and get two different masses is so that later on the energy equation can be subtracted off the other, where you can cancel off the heat loss. Remember, this one is actually in the part of your notes. You actually had to use two different power settings, have two different value of masses, so that eventually you can take one equation minus off the other in order to cancel off heat loss, so that you can find the specific latent heat of vaporization. But at the same time, this one can only be done if you had same exposure time as well as same temperature difference. In your case, you're actually doing that already. You see your inlet outlet temperature are the same. You actually have something like same temperature difference. And then because you're doing it in terms of per second, it's kind of like same time also. All right. So why would you actually obtain two values of M rather than just one value? You would just say is mainly to account for heat loss to the surroundings. Or you can actually just say to cancel heat transfer or heat loss from the tube or surroundings. Okay, yeah, it doesn't matter whether you say heat loss or heat gain over here. Okay, because you may be wondering, this one is 25 degrees and 19.5. How do I know whether heat is going in or whether heat is going out? It actually doesn't matter. You can either just say heat loss, you can either just say heat gain. That's why the marking scheme answer allowed you to say either one. Okay, just pick one. In my case, I just say heat loss. You can either just very simply say that is to account for heat loss to the surroundings or to cancel heat loss to the surroundings. Okay, but what you should never ever write is to say that it is to stop or prevent heat loss. Heat loss will still be present. You are actually not stopping or preventing it. But what you've done is that you have somehow taken into account so that you can cancel it. Okay, so be very careful about the terms that you use. Do not ever say is to stop or prevent heat loss. This is different. It is implying that there's no heat loss occurring whatsoever, which is not true. It is occurring. Just that you have found a way to take it into account and to cancel it. Okay, right, so that one out of the way. The last part is talking about some calculations. Okay, the calculations will be something that we can do very quickly. Now, they ask you to calculate the specific heat capacity of the liquid. Okay, you will actually do a method that is similar to what we've done in the notes, but this time is applied for specific heat capacity, not for specific latent heat. The ones that you saw in the notes was to find specific latent heat. Okay, and the past years you actually done the same to find specific latent heat. But this current question is not really so much on specific latent heat. It's really asking you about the specific heat capacity. But the method will still be the same, like what you did for latent heat, where you had to find two different energy equations, find two different masses, and then take one equation minus off the other. So here, you can actually say that, wait, let me just write it out. You can actually just say something like this, huh? Heat supply by heater is equals to heat gain by liquid plus heat loss to surroundings. Okay, so you're using this energy equation, okay, which is applied over here. But in your case, you don't write it in terms of just heat energy, you write it in terms of heat energy per unit time. Okay, they must be in per unit time because your answers are actually all in per unit time here. See, your energy here is energy per unit time. Your mass here is mass per unit time. Okay, so you write them in terms of per unit time instead. Okay, so if I try to write it out for you, it basically just means this now. E is mc delta theta plus heat loss divided by T. This one will become E over T equals to M over T C delta theta plus H over T. Okay, but coincidentally, E over T is already your power. Okay, and this one, if you look at the question, mass per unit time is actually M itself. Okay, that's why here I can write them like this. For the first situation is P1 equals to M1C delta T plus H. P2 is M2C delta T plus H. Okay. Yeah, this one also H over T. I actually just wrote it as H now. It doesn't matter actually because you see they cancel off. All right. So take equation 2 minus equation 1 or equation 1 minus equation 2. It doesn't matter. You get P2 minus P1 equals to M2 minus M1 times C times delta theta. So just sub in all the values, you will get your answer as 4.11 times 10 power 3 joules per kg per Kelvin. Okay, now in your current case, this one you need to be careful about your units because you see joules per kg per Kelvin. The methods that you have is in terms of gram. This one you have to change it to kg. Okay, because because the units here you see there's no such thing where there's no other term that can cancel off the gram. Okay, while the gram remains inside your equation, it will carry over to your final answer unit. So you need to make sure that the gram is changed to kg. Okay, that's why you see here there's a times 10 power minus 3 because you're changing gram to kg. You divide by 1,000. Okay, so you're going to get the answer as 4.11 times 10 power 3. All right, so this one would be your answer. Okay, very straightforward. Now, if you look back at the notes, sorry, not the notes, the worksheet, I believe you have another part here. Okay, now part C you cannot do because this one is actually related to a different chapter in A2 called AC circuits. You cannot do this one at the moment.